Hey, this is Mr. Mitchell. Let's talk a little bit about magnetism and electric currents. There are the questions. Here's the content. Yes, there is a relationship between magnets and an electric current. Now, it wasn't really discovered much by the scientific community until about 1820, but even before then, a lot of people kind of had a suspicion that magnets and electric currents had some relationship. After all, whenever lightning strikes, it can change the direction of a compass needle, and in a thunderstorm, iron pans sometimes become magnetized. So, what is happening when you have, electricity, for example, going through a wire? When you have electricity going through a wire, or even just the charge of ions, you do have a magnetic field around it. And you can see in this picture kind of the diagram of the magnetic field that goes around it. And this magnetic field is positive ions. So it would be attracted to things that have negative ions. But kind of the point here of what's called the right-hand rule is the right-hand rule tells you what direction this magnetic field flows. You can see if you hold the thumbs up signal next to the wire here, if you hold the thumbs up signal to it, the direction would go in the same direction as your curled up fingers. The curled up fingers have the flow, show the flow direction of the magnetic field. So anytime you have any wire with electricity run through it, you have a magnetic field around it. Yes, that applies to stuff you have plugged in at your house. Yes, that applies to batteries. So how come we don't feel it? Well, it's a very small force. It's not very strong. But we'll see in a little bit how that force can be expounded and made really, really big. So let's talk about a compass more. What happens when a compass needle is brought near a magnetic field? Here you have a compass, you have the north end here, that is attracted to the south end of this magnet. Here you have the north end here, but it's not the north end that's attracted to the north end, it's the south end that's attracted to the north end. A compass needle turns toward a magnetic field. Not a strong force, just like it isn't with over here in the wire, but it is there. The larger the current, the stronger the force to steer these magnets toward it. Well, anyway, I have another design here. Here we have a wire, and there's no current running through the wire, so you have all these pointing to the north. But notice what happens whenever you have this wire which has a current running through it. Look at what the direction of these compasses. They are going around the magnetic field. So the compass is actually pointing in the direction of the magnetic field right there. The larger the current, the stronger the force. If you have wire that's wrapped into a coil like you have down here, then it has an even stronger force. Send electricity through this and it has more of a magnetic field. In fact, a considerably higher degree of magnetic field around it, you might say. This is called a solenoid. A solenoid is whenever you have electric current running through a wire coil for the purpose of making it magnetized. It even has a north and south end to it. One side would be more positive, one side would be more negative. Now there's a way you can make this solenoid even more powerful by inserting an iron rod into it. And here's an example of it, and it's called an electromagnet. Here you have this coil, send electricity through it, and you have an iron rod in it. You may remember that iron rod can be made magnetic. And in this case, with the current running through it, it makes it even more magnetic, and it makes the wire even more magnetic just because of its presence there. This is called an electromagnet. Now look at these other electromagnets here. This magnetic, electromagnets, my bad. Here you have the wire going around this iron nail, and it makes for more power than it would have if just the wire were by itself, or even if it were just a solenoid. And take a look at this one up here. This has a huge degree of wire going around what looks like a very well established iron bar. These are called electromagnets. Electromagnets really can influence a lot of the, what's the word I'm looking for? Can't really come up with it, but it really influences some of the inventions that we have that we kind of take for granted. They have electromagnetic magnets in them. Now, this kind of brings up the point, since you have this iron bar here, which is not magnetic until it has a magnet around it, as to what is magnetic and what is not. All magnets are created by movement of charges. Now, in theory, everything has movement. I have an example here. Here's an atom, and protons or neutrons are in the nucleus, and what do you have flying around it? You have electrons that are flying around it. These electrons are causing movement in every object. The desk you're sitting at, there is movement in it, even though it looks still at this level. Same thing with the sofa you may be sitting on. There's movement there on the atomic level. So in theory, this electron spin would cause pretty much everything to be magnetized. But you and I know that everything is not magnetized. In fact, it's only a few things that are magnetized. Here's what scientists think. They think in some cases the electron fields of an atom cancel each other out. And that means the material is not magnetized. But in items such as iron, nickel, and cobalt, not all of the magnetic fields cancel. So that's why scientists think some things are magnetized and some things are not. That brings us to the term called domain. Domain is where groups of atoms are aligned in a common direction. When that is the case, like in this diagram here, when that is the case, magnetic fields can sway these domains toward its opposite charge, and it would make it magnetized. So if we have some kind of magnet here, since this atom here has domains of atoms facing in the same direction, it is more likely to become magnetized. Atoms that are unmagnetized and do not have domains of atoms facing in the same direction are less likely to be magnetized. So that's kind of a heads up on what that is. Let's take a look at this term galvanometer. A galvanometer detects and measures the amount of current flowing in a circuit. You know, we've talked a little bit about voltage, and we've talked a little bit about amps, and we've talked, well, that amps are part of current. So it measures in ammeters, that measures the amps, and we already know about the potential energy is in volts, but it also measures that potential energy in something called voltmeters. Now, these galvanometers use an electromagnet. You may remember that an electromagnet looks something like this. These are electromagnets. It uses an electromagnet to determine how many ammeters and voltmeters you have. And you can kind of see here that the current is flowing through this electromagnet area. You have the coils that are wrapped around. You have an iron bar that is flowing in, that is in between. And it measures, the more it measures, the more it will turn the galvanometer. It will turn that electromagnet in there. And that will show you the degree of ammeters and the degree of voltmeters. The greater the current, the stronger the electromagnet's magnetic field, and it rotates the lever more. Now, we actually get an magnet in electric motors. I'm sure you have seen electric motors. An electric motor looks, well, I guess the most common one you might see is something like this. This is a very small motor, but you can see you have the ions that will be flowing in these cords here. And here's a little bit bigger electric motor. And here's a real big electric motor. And I guess you don't have to read all of this that is around it, but you can see you have the electricity that is coming in and that is leaving. You can see that we have the electromagnet in the motor. So we have the iron bar here, and we have the coils that are wrapped around it here. It looks like it's something solid, but it's coils that are wrapped around here. So this electromagnet makes the electric motor. Now here's just a little bit about it. Electric motor spins coil with an electric current. So electric current goes through here, through these coils, and the shaft is attached doing whatever desired work it is. And this particular thing here will spin. Whenever you have the electricity running through it. There is something called a commutator and brushes on an electric motor, and they can reverse. They go back and forth and back and forth. And what happens is the magnetic part of this, this makes a magnetic field. What happens is the fact that this is reversing will constantly have repelling going on. So whenever it's constantly repelling, that keeps things turning. It keeps things turning whenever you have the constant repelling going on here. So it keeps this going back and forth. Motion caused by a magnetic force can produce sound waves. So here we have this electromagnet in here. We have the coils around. We have the iron bar here, or whatever permanent magnet we want in there. So we have the coils that you send electricity through it, and it makes the whole thing vibrate. So it can produce sound waves. It's wrapped near the cone, or wrapped with the cone around it. Cone is attached here. So when the current runs through, the magnetic field causes it to move. That makes the cone go in and the cone go out. When the current is reversed, the cone moves in the other direction. So cone goes in, current is reversed, cone goes out, and it makes the desired waves. And you can see that we have the magnet here. That's the electromagnet, which is right here. You have the coil, which is part of the electromagnet, and the cone that vibrates when the electromagnet sends it in and out. Well, I hope you learned a little bit about electricity and magnets. And hey, don't forget to read about this in your science book.